Welcome back to the second part of lecture 3. Where we left off was we were with this nice consequence that every elementary row operation can be represented by a matrix multiplication by an elementary matrix. Now there's actually another very useful fact is that every elementary matrix is itself invertible. And not only is it invertible, the inverse is also an elementary matrix. And the reason that this is the case is because you're just undoing the row operation. So you're just undoing a single row operation, but that means you're just doing a single row operation on the identity matrix. So for example, this matrix here was obtained from the identity matrix by multiplying row 3 by 5 and adding it to 1. So we want to make this a 0. All right, so we're going to reverse what we did. So the inverse of this matrix, the inverse, is going to be reversing this idea. So 1, 0, minus 5, 0, 1, 0, 0, 0, 1. Okay, so instead of adding 5, we want to subtract 5. So we have row 3 times minus 5 plus row 1 of the identity matrix. Similarly, if we originally formed our elementary matrix by multiplying by a single constant, we want to undo it by multiplying by 1 over that constant. So the inverse in this case is going to be 1, 0, 0, 0, 1 over 6. Oh, sorry, that's a poor 6, so let me make a nicer 6 here. 6, 0, 0, 1. So this is row 2 times 1 over 6. And you can check that when I multiply this matrix by this matrix, I get the identity matrix. Now, using the language of elementary matrices, I can prove this very important theorem. And this theorem is saying that if I have a square matrix, it's invertible if and only if you can row reduce that matrix to the identity. And now I forgot to put the A here, so let me put that in. So an n by n matrix A is invertible if and only if A can be row reduced to the identity matrix. And let me give you a proof of this fact. I'll try to go through this slowly to show you all the details. Okay, so one thing to pay attention to is that this is an if and only if statement. So there's two directions that we need to prove. So the first direction, we're going to assume that A is invertible. Suppose A is invertible. Our goal is to show that this matrix can be row reduced to the identity matrix. Now we're going to use something from last class. Last class, AX equals B, this matrix equation, has a solution for all vectors B in Rn. Because it has a solution for all B in Rn, what this means is when you put the matrix into row-reduced echelon form, it will have to have a pivot in every column. Excuse me, every row. So A has a pivot in every row. But then A will actually have to have a pivot in every column. And the reason for that is because the matrix is square, since A is n by n. Right? Because if it has a pivot in each row, it has to have n pivots, and one in each, and each pivot must be in a different column. Since there's exactly n columns, we have to have a pivot in each column. And that means, so A reduces to the identity matrix as required by the statement. So that's one direction, and it kind of uses some of the results from last class about the inverse of a matrix, namely that you can solve this system here for any vector B. What about the reverse direction? Well, because A is row equivalent to In, we can reduce A to In via basic basic row operations. Okay. Now, sometimes when we do these, on paper, in practice, we can do a whole bunch of row operations simultaneously. But say that we're doing it very explicitly. We're doing one basic row operation at a time, and we can keep track of that. So A is equivalent to A1. We do another row operation to get A2 all the way down to some sort of matrix AT, which gives me the identity matrix. What we saw kind of from the first part of these lectures is because these are basic row operations, each operation can be represented by a multiplication by an elementary matrix. So each operation can be represented by multiplication by an elementary matrix. That just follows from what we were discussing earlier in today's lecture. So we can kind of keep track explicitly about what's happening here. Right? So let me show you this. A1 has to come from multiplying the matrix A by an elementary matrix. A2 comes from taking A1 and multiplying it by some sort of elementary matrix. And we keep track of this all the way down. AT is equal to taking the previous matrix, AT minus 1, and multiplying it by some sort of elementary matrix. And remember that this is going to be equal to the identity at the end. Okay, well, what does this all mean? All right, so let's put the pieces together. We have, so IN, this guy right here, is equal to, well, if we do start doing substitution, notice that I can take this expression for A1 and I can stick it into here. So A2 becomes A2 times E1 times A. But then I can take this expression and stick it into the expression for A3 and so on. So we end up with the identity matrix can be written as a product of elementary matrices times the original matrix A. So we can get the identity matrix by first doing this elementary matrix, and so on. Now we use some of the facts that we kind of said earlier, namely, each EI is invertible, right? So it has an inverse, right? So AI inverse exists. So what we're going to do is kind of get rid of all of these identities on or elementary matrices on one side and push them to the other side. So let me write this out so you can see what's happening here. So take this expression right here, and what we're going to do is have, and make sure I put it in the right order, E inverse 1, E inverse of E2, all the way up to the inverse of ET times ET, ET minus 1, E1A. And so what I'm doing is I'm going to multiply both sides of this expression by this matrix right here. So, and it's a giant matrix, but that's okay. Okay, and now let's look at what's happening on this side. Notice that these two guys here, because they're beside each other, they get pushed together and they become the identity matrix. But then this guy here will get paired up with this guy right here. So when they get paired up, they become the identity matrix. So everything here will, on this side here, will start collapsing. They start killing each other. And at the end of the day, on the left-hand side, you will have A. And on the right-hand side, oh, there should have been an inverse right there, you end up with this matrix right here. So I'm just dropping the identity. And now we get our conclusion that we wanted. So A is invertible since it is a product of invertible matrices. Oh, and it's a good thing I finished the proof because I ran out of page room on my sheet here. So I'll put my little square right there. So this is probably one of the more complicated proofs we've seen so far, but it's an important proof because it shows you how if you have an invertible matrix, it's row equivalent to the identity and vice versa. Okay. Now, why do we care about this? Well, the whole point of this theorem here is it justifies why the procedure from last class works. Right? At the end of my proof, I showed that A is equal to the being multiplied by all these inverses. Now, what can we do with that? Well, what we can do is we can take the inverse of both sides. Okay, so we take the inverse of both sides. Now, the left-hand side here just becomes A inverse. There's nothing surprising about that. This guy here, remember what I called the socks and shoe property, reverses the order of the multiplication. So it goes the inverse of ET time to its inverse. And then I have the inverse of ET minus 1 to its inverse, all the way up to E1 inverse, inverse. But all of these inverses start to all cancel themselves. So we get ET minus 1, all the way up to E1. Okay. So what we should be seeing here, and I'll summarize in a sec here, is that the changes, the matrices that are changing A to the identity are going to be changing the identity to the inverse. Okay, so I'll write that out for you. So the operations that change A to the identity, so what we have is IN is equal to ET up to E1. A. So by performing these elementary row operations in this order, we get the identity. Also change the identity to A inverse because we have A inverse is equal to ET minus 1 up to E1 times the identity. So when we put the matrix A beside the matrix identity matrix when we do the procedure and we perform the operations on A to get the identity, at the same time we're performing the operations on the identity, and when we get to the identity on the left-hand side, the right-hand side has to be equal to the inverse. So as I said right here, this justifies why the procedure works. So I hope this explanation makes sense, and at the very least, you should be very comfortable using the procedure to find the inverse. In the next part of my lecture, I'm going to talk about the classification of invertible matrices.